From ContainerDays Hamburg, this video is proudly presented by DAX IT.
Quick question before we start. Who attended the talk yesterday about K8GB? Just show of hands.
Okay, not too much.
Okay, we won't tell that many people stuff they already know. That's good.
All right, then thanks for joining our talk. So my name is Toby. I'm working as principal architect for Kubernetes since 7 years and try to solve CNCF problems at our customers.
And I'm Nico. I work at Datev as a platform engineer and mostly provide internal Kubernetes platforms. That's the gist. So, load balancing.
Yes, so basically, what was our point here in the talk was basically we had an evaluation that we wanted to have a global failover scenario where we said, okay, we have multiple data centers, but we expecting a data center outage because of some physical things or cable cut or something like that, as we're running critical infrastructure with in a regulated market. We need to be ready to that we can distribute workload. And the target is to not switch over in a milliseconds, but switching over really in a matter of minutes automatically. The most important point is that this happens automatically. So, but before we go deeper in the global load balancing scenario, we want to give you a short introduction. What is load balancing about, really? Because I think everyone kind of using load balancers to exposing the applications, but not too much people are really deep in it and doing it. So what is the first thing? What is the basic concept of a load balancer? Basically, we have users, a lot of users calling one endpoint. That's basically your load balancer. Often, if you make a DNS lookup of your DNS name, you're getting a stable IP or multiple stable IPs, what hitting then a load balancer, and the load balancer distributing the traffic to different servers in the traditional world or to different clusters or different services. So here, basically, we try to distribute the traffic. How it works in Kubernetes. Basically, if we say we deploy something, we have a deployment, what creates a replica set, what creates endpods. In Kubernetes itself, every pod has an IP, but this IP can change when you're doing an update, then the pod getting another IP or another name. So you cannot access it directly. To have a stable reference of other service to calling your application, you need a service. This service is mostly cluster local. Internally, you can reach the service by a name or a stable IP. And when you then want to expose it outside of your cluster, you mostly need something like an ingress or for newer stuff, gateway API. In the ingress, you basically say, hey, if you come from the outside, this is the name. You can, we matching the name and then forwarding the traffic to the local service, and the local service distributed on across the pods. So, but how external load balancing comes in the picture is somehow the traffic must come internally. So basically we have, if we follow a request, we have, if we calling example.com, we have a maybe public available load balancer or a private network, doesn't matter, it's basically the same routing. The load balancer routes to the nodes of your cluster, and every node have a node port open and what points then to the ingress. Mostly people use an Nginx ingress, but it's the same concept for every ingress controller you're using, and this distributing then the traffic to the service and to the pods. How the reconciling works there in Kubernetes? You know, most successful concept in Kubernetes is reconciling. So you have a spec, in this case it's the ingress spec, then the ingress controller catching the spec knows, okay, this is the host name, what I should listen, and if I see this host name, forward it to the service. So it's basically what the ingress controller does. But we still have not an external load balancer. Why external? It's mostly located outside of the cluster. So basically, here we have a service type load balancer. If you spec a service with the type load balancer, you get in an external IP. This external IP and the external load balancer get created by the cloud controller manager. In example, AWS, you're getting an ELB. In Azure, you're getting an Azure load balancer. On-premise, maybe you're using Metal IP for ARP or BGP announcement, and you're getting a route to your endpoint. So basically, this is handled by a so-called cloud controller manager. And is this get maybe IP back from the load balancer, the IP get entered here to the service, the ingress controller connecting it, sees the IP, and the ingress component itself get the IP reference. This is often then used for other automations like DNS or certificates or something like that. Okay, so so much to the basics. But why we need load balancing? So first is we need to distribute incoming traffic. So we don't want to overload a backend. So we want to distribute the traffic. There are different protocols. We don't go in details, but for example, you can say every request get to another pod, or you say I have like a sticky session approach where you say one request from the same client should go to the same instance every time, and this should prevent that you overload your backend. Some load balancers have maybe also something like denial of service protection or something like that. One important point is health checks. So basically, your load balancer should detect, is the service still available or not? If it's not available, it should move it out. Why? Otherwise, you get a 404, service not reachable, and this is what you want to prevent with load balancer, that basically you just reach the healthy instances, not all instances. Yeah, precondition. So what is the load balancer precondition for? So basically, if you want to really deploy high availability services so that you can survive an outage, or you have zero downtime deployments, you need a load balancer because you're changing behind the scenes your backend, and your backend must be kind of available all the time. For that, you need a load balancer concept. Security is also important. It's protected backends like for different things. Often is surrounded by firewalls or web application firewalls. For example, the simplest is I open only the port HTTPS for the outside world, so I'm getting only this traffic into my cluster and to the ingress controller. The ingress controller maybe itself has some rules to protect it, and then it's forwarding my pod. So it's protecting with barriers that I only get the traffic to my pod what I'm expecting, and deny all other stuff. But be aware, your load balancer could be also the single point of failure. If it's down, maybe your application is happy, but if no one reaches it, you're still dead. Okay, so in a data center, you have basically two routes. You have the north-south route, where you say basically what I explained. You have a client going over the internet, you reach your data center endpoint. They have maybe several routers or firewalls, and there you have the load balancer distributing it to a sub-zone. And this sub-zone is often a VLAN, or have a dedicated IP space. But typically, all load balancers have feeds into this network, and you have a separate network for maybe other location. This could be your Kubernetes cluster, where they can talk to each other. And there you have the east-west traffic, where basically it's allowed to talk to each other, but this guy cannot reach this guy, and this can talk to each other. So that's the typical architecture. But why is this not enough? You saw it already? Because of that. So data centers are physical locations. There can happen something what you have not under control. The OVH had not so happy experience, I would say. But it's not like that's only like this disaster scenario. Maybe it's just you misconfigured a firewall or something, or some intrusion detection blocks you, or some outages of electricity or the load balancing itself. So to be aware about these risks, we need something like a concept of global load balancing, that we can say, okay, one failure domain phase out. By the way, for all public cloud guys, check out how often some regions are failing in the last 5 years. Also there, some AWS region completely get shut off. This also happens. So if your business is relying on it, be aware that you do a risk analysis. How risky is your scenario? Because, yeah, if you're just running maybe the lunch ordering service is not so important, but if the lunch ordering process is your main business as you are Lieferando, then you should care maybe that you survive such outages, because otherwise you're losing money. Okay, so the first solution what we evaluated to in the project was a cluster mesh. So basically, don't mix it with service mesh. A cluster mesh is something where you're connecting different Kubernetes clusters together in a network. And I want to show you how this works. Basically, what we want to achieve with the cluster mesh is a pod-to-pod communication, so that we have two clusters, and pod of this side can reach a pod of that side. So that's the basic goal. What you need for this is basically a layer 4 connection. So really node IP to node IP communication. What already is kind of a minus point in our perspective, because this in our case was one was an OpenStack data center, one was enabled AWS, and then one was on Azure. So need to peer all the networks with a side-to-side network or something else. And Then we need a load balancer service for the cluster mesh API server. So we use Cilium in this case. Maybe some other cluster meshes works differently, but mostly every works in the same way. So here we see that we have the cluster mesh API server, what coordinates what is running where. Basically, you have then communications or sys agents here talking to the cluster mesh API server. It's not a Kubernetes API server on that side, and the other way around. So they both can exchange information, who is running what. And this brings then basically the scenario, if you want to reach a pod on the other side, basically your agents knows, okay, this pod is not located here over eBPF magic, ask the Cilium folks how it works, forwarding it traffic to the other cluster, and then reaching there the endpoint. Therefore, you need to ensure, what I missed here is that the nodes have different IPs. And they are not using the same IP range. So basically that every node has a dedicated unique IP in both clusters. So that's really important to know. Okay, I think that's a basic concept. Now I want to show you how we're setting up something like that. In this case, we used our K8GB platform, created 3 clusters, and configured the Cilium CNI. The Cilium CNI itself has already the capabilities. By default, it's not enabled. You need to do a kind of a bootstrapping. If you just want to try it out, use the Cilium CLI, but of course it's much easier as the approach what I show you now. But we wanted to do it in a GitOps approach and want to really make it with like Helm values persistent, how we do it. But if you just want to play around, the Cilium CLI is much easier. It's one command mostly. If the prerequisites are there, you can do it. So what we need, 2 clusters in this case. We have the Cilium operator, what gives you your Cilium CNI daemon set, and you need a connection. This connection you can achieve by a WireGuard, VPN, or a side-to-side connection, or if you are in some same broad network, you can just need to reach that one node IP can reach the other node IP of the other cluster. Then we do a bootstrapping and say, first thing is, my pods need a dedicated, distributed pod sider, because pods on cluster A cannot have the same IP as in cluster B, otherwise it's not working. So you see it's already some management of IPs, what I don't like personally. So if you are thinking about mesh everything, maybe it's not smart because then you have a lot of IP management to do, and also you open all connections to all clusters. This was kind of a downside of this approach. What is then the bootstrapping doing? Basically, we enabled the cluster mesh API server, and there we're getting a service type load balancer for the API server. This is done by this configuration. We say we're giving a name in our cluster mesh, say please create a TLS certificate. Then we configured the same stuff on the second one, what then reached the first one, and you see it's getting already complex. We have then the second one giving also a name, and there we're giving the CA certificate for knowing, okay, we're doing mutual TLS between the 2 cluster mesh API server, and they need the same CA. And then we basically say, please reach cluster 1 on this endpoint and authenticate yourself with these TLS certs. So then, basically, we achieve the connection from this cluster to that one. Next step is the vice versa. And you see, if you have multiple clusters, it's getting more and more complex. You need to do every cluster, make aware on every cluster. So that can be quite a little bit of a challenge. There, you can figure then this Cilium setup that to reach the other cluster. Basically, the same stuff, CA, and client server authentication and the name and the endpoint of the cluster API server, and then you finally have your cluster mesh. So wasn't it easy? And then you're checking your health status, and if everything is fine, you can talk to each other. Then you have routing strategy, what can do. Basically, you have 2 things. You can say either I want to reach one service what is dedicated to either your local cluster or your remote cluster, or you say you have a failover scenario where you say, please reach first local service, and this is not reachable, go to the remote thing. What is our preferred way? We say, okay, this is a service we want to get reachable from the other cluster if this cluster is down. And here are the annotations. There are some routing things. You can look it up in Cilium documentation. And if you want to try it out, go to the Cilium lab. It's really cool made, really easy to follow. Shoot out to the team of Cilium, really great implemented to try this out. Cool. but what is about our DC outage? So basically, we have the scenario, we have 2 clusters, and we have 2 entry points, what we match then with a DNS entry, and then we say, okay, if this workload is identical, in this case, it was a stateless workload, so basically, we need to reach our backend, and our scenario, the first scenario, we just killed the pods. Then, if you reach this endpoint, traffic get forwarded to this cluster, failover worked, great. But then we said, okay, let's simulate the DC outage. So basically, we destroyed the complete cluster and see what happened. Basically, then we see, okay, Mr. Cluster Mesh, we came not to the approach what we expected because it needs a running Kubernetes server, Kubernetes control plane, a Kubernetes cluster. The workload must not run, but the cluster itself must run. In this case, we destroyed everything. Then your request just stuck here in the entry point and nothing happened anymore. And you have 50% of your data, of your request lost. This brings me then to the next topic, what Nico will present.
So as we just heard, yes, it is load balancing, yes, it is cross-cluster, but I wouldn't quite call it global. Let's start with what we already discovered. Hey, just treat the world as our availability zone, because even if we have the data center 1 and data center 2 in Frankfurt, for example, if one burns down, the other might not be too far away. So, quickly, if you have your favorite load balancer provider, cloud provider, you can also just buy it from them, because everything I'm going to show you now, it works, it's cool, but it's DNS. Spoiler, it's DNS. And it's always DNS if something is broken. So most of the cloud providers already have stuff like this. If you don't have a team of at least more than 3 people, please don't do it in production. So, as I said, it's DNS. Why is it DNS? Well, you all know DNS. We ask our favorite DNS provider for some domain name, and it returns an IP address, maybe IP4, maybe IPv6, and then we talk to the server directly. I think I don't have to explain it any further. So, what can we do? Well, we introduce some kind of health checking. We make the DNS server smart. It's not only a static zone file, but we tell the DNS server, hey, please check if our servers are up. If one of the servers isn't up, only respond to the user with the IP address of the server that isn't down. So we basically make our DNS smart and don't really have a load balancer itself, but DNS handles everything. And this is where K8GB comes in. It's an open source CNCF project, and it allows us to automate this process. How does it help us? Well, at the end of the day, K8GB is a small operator that interacts with core DNS as the DNS server and external DNS, and it checks the statuses of our Kubernetes services. So it just uses your normal pod health endpoint to check if it's up or not. That already makes it pretty easy for us Kubernetes folks. External DNS is used because we use DNS delegation. So our zoneexample.com, the subzone of that, test.example.com that gets delegated to the core DNS server, and core DNS now handles all DNS for us. Okay, now it's still one core DNS. No. Every cluster we want to use in our global load balancing has its own set of the service we deployed, and of course also core DNS, because our main DNS just delegates the zone. So we just have, for example, here 3 name server records that point at those 3 core DNS instances in the different cloud providers. And when the client comes in and asks, hey, where is my demo service? Our main DNS says, hey, please ask core DNS, and core DNS tells us, hey, please look over there. The different K8GB instances also check each other, so that's how basically they know, hey, do I need to fail over? Is this request for my local pod? They do periodic checks. You can set them to whatever you want. The default is 30 seconds. So that's all pretty nice and well. Let's just have a quick look at it. We won't go too deep into the entire installation, but it's a Helm install, and you just plug in your zone name. So over here, we have just watch running dig, and these are the IP addresses of the normal cloud load balancers of our 3 clusters. Then we get the call response from our demo server. So see it's hello from Data, hello from GCP, or even hello from Kubernetes. And in the bottom right are our pods in our main cluster. The entire configuration, as I just said, is stupid simple. We just, right now, I just have it set to round robin. So I tell it, hey, please look at this ingress object and do round robin. And I even did weighted round robin. So as you might notice, the dative answer should be the one you see most often, followed by GCP. And then Kubernetes just sometime randomly shows up. This is pretty awesome if you have some regulatory requirements that need this. At my company, we sometimes need to split traffic to different cloud providers because otherwise the German financial institutions get pretty sad pretty quick. Of course, usually you don't want to do round robin, so we can just say, hey, we insert failover, for example. Let's say failover for 1, so cluster 1 is the primary. It just applies the config, and bam. Now we only get answers from our dative cluster. To switch over, we could just tell them, hey, please set the primary to 1, but that's pretty boring, so we just kill the service in cluster 1. As you see, there's a short delay between the actual switchover. I set the DNS time to live to 1. So it's pretty quick. I wouldn't recommend it in production. Usually, if the failure is this catastrophic, you can survive a couple of seconds of downtime. So now our new primary is cluster 2, and if cluster 2 also fails, then we switch over to cluster 3. And as soon as we start our service again in our cluster 1, it takes a couple of seconds. As soon as the pods are running, it should start to answer, yeah, here it is, dative cluster 1. Pretty stupid, pretty simple, and it works with normal technologies like just DNS. And the failover config is even simpler, even stupider. We just take our same object and insert type failover primary cluster 1. We can add as many clusters as we want. The one gotcha is that we have to tell every cluster, hey, you also know cluster 2, cluster 3. Of course, you don't have to number them. It's just because I was a bit, I didn't want to get creative. And this is basically how it works. But this is the demo video, don't worry about it. I prayed to the gods and they answered. The awesome thing about this is we're using standardized open source technology. For example, CoreDNS. CoreDNS has a bunch of plugins. For example, the Prometheus plugin is always enabled for a zone. So you can add your Prometheus exporter and Grafana or whatever you like to use and see the metrics for the resolutions and stuff like that. And in my case, you can enable DNSSEC because most of the cloud provider solutions, for example, the solution provided by Azure, don't actually support DNSSEC. And at least my DNS team always gets pretty sad when something doesn't support DNSSEC. So in this case, we can just ask Delph, and it will respond with fully validated. For the records for our first cluster, of course, if we set it to round robin, it will return multiple IPs. I think I have a screenshot here. So if you set it to round robin, all the DNS entries are validated. You can use the GeoIP functionality. Everything you love about CoreDNS is basically supported. But how about the real world? I don't only run some funny echo service that says hello from data center. That's sadly not what happens in the real world. We always need some kind of state, maybe a database or something else. I have a quick example that we actually sketched up and also tried out at my company. We have clusters and we have local registries in our data center. And maybe only the registry fails, but the clusters themselves survive. But because the registry is down, users can no longer pull image, so the entire data center might as well be burned down. No difference to the users at the end. So why don't we just add some kind of load balancing, for example, K8GB, and do health checks and tell all of the clusters, hey, please use the central domain name as your registry. In containerd, you can also set the primary to the local data center one and then a mirror to the one in your cloud environment. And the nice thing, most container registries nowadays support some kind of sync, so I don't have to think about that. In this case, we tried it with Harbor. Harbor has some peer-to-peer features. Of course, if you just have a database, your database probably supports some kind of replication strategy among data centers. It is still application specific, but you can do it. Most of the time, developers just don't want to. So, what will we learn? How did our solutions compare? There's a big, nice overview slide for you, but I'll tell you the gist of it. Cluster mesh, pretty cool. You have fine-grained control over traffic for this one service, this one pod, and of course, you have mutual DNS beefing everything. Cilium is also not the only provider for it, but we use Cilium because it was the easiest to set up in this case. You have pod-to-pod communication across clusters, but as Toby said, you either need a VPN, some kind of direct mesh, or even a really, really large network for them to talk to each other. And the TLS handshaking, yeah, it's okay. The setup is pretty involved. The Cilium folks promised that it will get better in the future, but the future is not today. On the other hand, with the global load balancing via DNS, we have a pretty simple, pretty bulletproof solution. DNS itself works, if you configure it correctly, of course. And we can either fail over automatically, or we can tell that, hey, this is primary 1, this is primary 2, for example, if you have to perform some maintenance on one of your data centers. It is globally scalable, not just with your one cloud provider, but across any cloud provider. Another big topic that regulators love around here. And you can even introduce geo-aware routing based on geo-IP data and core DNS to route your users to the nearest data center and then fail over if something goes wrong. You have to host your own DNS. Some of your company's DNS teams might like this. Mine complained a lot. But hey, at the end of the day, they have to help us if it's the only viable solution. And you have DNS caching. Your browser caches, your client caches, maybe your local router caches. Right now, the failover was very, very fast. But in the real world, you have to allot half a minute up to 5 or 10 minutes, depending on your setup, for users to fail over. So it's not a magic bullet. And you can't just say, hey, service in cluster 1, the database you need is in cluster 2. Doesn't support it. But we can combine them. And this can lead to very, very, very little downtime as long as we only kill the pods. So if in our cluster 1, everything dies, all of the pods die, but the cluster itself is still running, cluster mesh can take over. As soon as the entire cluster and the entire control plane is dead, now it's K8GB's time to shine, and it itself can fail over. So they extend each other, they don't really collide. And there are more awesome projects.
Maybe one point, what I want to point out from an operational perspective.
Yeah.
If it's night, 3 a.m. in the night, you don't want to debug cluster mesh, I guess. DNS entry to overwrite it to another endpoint, you can do still. So basically, this is one of the main advantages. You can just simply write with one DNS entry point, control your traffic. Also, if all operators are failing, you still can do it manually. And this is what makes it simple, and also for a disaster recovery or failure scenario, easy to fix. That's really important, because in these cases, you maybe not are in the best mood, or you not have the experts there, but if you can override it simple, it makes you less downtime.
Yeah, so you don't ever even have to get woken up if the DNS team can just manually go in, update the record. They don't even have to know about all of the K8GB stuff.
Exactly.
Basically. So, of course, we need some kind of multi-cluster scheduling. There are a bunch of awesome open source projects that help you with multi-cluster scheduling and cloud bursting and stuff like that. We tested some of them. We tested Admiralty during our proof of concept. It wasn't our main focus, so I can't tell you that much about it, but the basic stateless service worked. That's all I can say.
Yeah.
all of the other ones should also work fine. You can also just roll your own multi-cluster deployment with Argo or Flux or something like that. You can even put it in pipelines if you want to suffer, but everything works out.
So here's the use case. If one cluster gets full and you have another cluster, you have still space, that it automatically scales up in another cluster to get you more power of it. So this can help even if you are on different data centers. Maybe the other data center has more capacity, and then you can scale out there.
Yep. That's where the weighted round robin comes in, by the way. Really handy. But that's the gist of it. Thank you for attending. This is the QR code with the link to the slides and the Git repository for the demo. And I think we still have time for questions, don't we?
Why have you not just multiple control plane nodes in multiple geographic zones for one cluster, plus Cilium, BGP, plus Cloudflare channels instead of multiple clusters?
Yeah, this does work, but latency. Latency is the one thing that will kill your etcd as fast as just deleting it. If all of your regions are local, pretty close to each other, valid setup. For example, at my company, we have multiple data centers. The latency between them is not that bad, so we can run stretch clusters, stretch control planes, and stuff like that.
That's the next question already, so don't be confused. You can still finish the first answer if you want.
Yeah, so Calico, no, we didn't try it in the scope of this talk because we wanted to use other Cilium features, but I'm pretty sure you can also use it.
The next question is related to one of the talks before. Why not to use grow or cross-plane compositions for the job?
I mean, here you have the same thing. If your cluster is completely down, no crow is running anymore, and who does know what other clusters are available? So this is mostly not about workload scheduling. It's more about how the traffic will flow. So this don't helps you in this case. Basically, if you see really not just the workload pod is down, so the full control plane, full data center is shut off.
Did you evaluate any cast instead of DNS?
I'm not.
No, we chose not to because it wasn't the right fit for our scenario because some of the stuff isn't actually really internet reachable or routable. So we needed a solution that didn't use any routing or IP-based strategies. If you're big enough and have smart people that know everything about BGP, Anycast, yes, cool solution. This is the solution for the small guy.
Yeah, another question, but kudos to you. Thank you.
Was a pleasure.
What are the limitations to this solution, and what challenges came up? Can you tell?
Limitations basically is the DNS protocol itself. So the switch over is limited to DNS, what it can deliver with TTL. And what challenges was basically to getting really DNS zone internally and getting the right DNS server guys convinced that we can set our own DNS names for a zone. And this was basically organizational challenges. Nothing else by K8GB, it was really cool, I must say. The setup was really quick. Cilium cluster mesh, there was the most problem was really to achieve this routing between node to node in different cloud providers. So you need a really more complex network setup with that you're getting access from the data center to the public cloud, to the other public cloud, and have this round robin, not round robin, but direct connection to the nodes.
Direct connection, yeah.
So you have now DDoS protection, right?
No, it's hidden because we don't have a global DDoS protection. But if you look back, for example, at this, the DDoS protection and firewalling stuff sits in each data center.
They don't see the slides.
No, they don't see the slides. That's sad. Okay. So basically, you have to think about it. You have your data center. You need some kind of ingress or load balancer in your data center, and you can either before the load balancer or inside of your data center deploy your favorite firewalling, web application firewall, something like that. And then you have DDoS protection.
Thank you for the answer. Well, this is just a re-implementation of DNS GSLB. A lot of commercial LBEs offer. Have you checked if you have violated any patents?
Sadly, I'm not one of the maintainers of K8GB, so you have to talk to them. I know that they work closely with Infoblox because the first upstream provider supported was Infoblox, so you have to talk to them. But since this is just setting DNS records, I wouldn't worry.
There was also some comments from F5 guys, so I don't know, but we are not legal.
We are not legal experts, don't ask us.
So, and for now, it was more like how to get it done. We currently don't run it in production. This will be the next step. Just to be clear, this will be then a validation what we need to take.
I think we have still a few questions left. Unfortunately, we don't have any time left. I think many of us are waiting for the lunch. Maybe we can meet you for some discussions.
Yeah,
of
we
course.
are here. Say, come around.
Just come downstairs, ask questions, or meet later. Thank you.
Thanks.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.